All right, hey there. So I'm just here briefly to talk to you guys about circuit fabrication. So as we've been seeing a lot in this course, we've been doing a lot of simulation of circuits, and not so much really actually building circuits. And so, there may be some questions about what do we do when we actually want to take what we have designed and make it into something real. So first step, just like we're doing in this class, very often you're going to be simulating circuits to get a good idea of your general design before you even go to start building it on a circuit board or on a breadboard. Um, Now you may skip this step and just jump right to building it on the breadboard as long as your calculations beforehand have given you a pretty good idea of what you want to build. But generally, people are going to try to simulate things first because it's a lot faster. So then you move on to something like this, where you're using a breadboard, and you can put some resistors in, capacitors, whatever circuit components you're using, put them all on the breadboard, and then you're going to want to test, verify your design, make sure that everything's working, right? And so you guys should have seen some TAs doing this in different videos, and maybe if you had a special interest, you may have done this yourself a little bit for some of these circuits. You may have tried to build some of them either with a TA or with your own home lab kit. Great. So that's great for testing, and that's great for what we're going to do in this class, right? Breadboards are great because they're temporary and cheap. I can use, this same breadboard for all the circuits I'm ever going to design, and I don't need to buy a new one every time I'm making something new. And I can reuse those components, right? Once I'm done with a circuit, I can take out all the resistors and use them on something else, right? So that's why breadboards, and simulations, these kind of tools and strategies are great for prototyping. But as we've seen, breadboards are not the most reliable, and they're pretty big. This is much bigger. If I'm making a small circuit, I don't want this whole breadboard sitting around just taking up space because that's all that I have, right? And it's a huge waste of space, it's a huge waste of resources, and it's a huge waste of cost, right? If I am sending a circuit into fabrication, into production, as a real product, and I have to make a breadboard for every single one, that's a ton of work just for a circuit, right? So the next level of abstraction that we may take away from our breadboard is actually getting down and soldering a circuit, right? And I believe Benjamin's going to be talking a little more in depth about soldering and how that's done. But the idea of that is basically we're going to be actually connecting components together. We're going to be using some soldering paste and some liquid metal, basically, to solder different components together and make our circuit. Now, this is actually pretty common, and some circuits in production are just soldered circuits. They'll take some, either like a neutral board, or sometimes even the circuits are just left hanging and they're just connected by different wires. So you've just got a bunch of hanging circuit components floating that are connected via wires and soldered together. So that can work sometimes. But again, we have a case, larger form factor. It's, a larger space because we have to have all our components laid out like that, and less reliability. If they're all hanging, you could run into cases where, they bump into each other, or the wires make contact in weird ways, or our solder could wear down and break apart, right? So that's not the best solution for larger, more complicated circuits, especially when size is really an issue. So the most common thing that we are going to use in chip fabrication is called a PCB. So PCB stands for printed circuit board. So it's a circuit that is printed. It's pretty self-explanatory, right? So we just have a circuit that's going to be printed onto a chip. Sort of like, it's like a digital document printer or like a 3D printer, but for circuits. So I'm going to show you guys a quick example of what we can do with a PCB and sort of the power that we have there. So I'm going to show you. So this over here in this window is a tool called Eagle. This is, I believe it's, oh gosh, who makes Eagle? It's the same people that do Fusion 360 and all of that. So it's a very, in case you guys have used those kinds of tools before. These are very common tools for industry, for lots of different engineering um, things. It's Autodesk, that's the name. Autodesk is the company that produces Eagle and Fusion 360, and they do a lot of work with fabrication. So this document that I have here, this is called a schematic, right? And it might look a little alien here at first, but I want to zoom in a little bit and see exactly what we're working with. So the main thing to see is that we have a lot of really familiar symbols, right? We have resistors. You can tell those are resistors. We can see how they're basically wired together here. Here we have some capacitors. These seem to be dielectric capacitors, or they seem to have some sort of polarity. That's why one side is curved, most likely to indicate the negative side. We have a lot of capacitors. There's some more over here. These guys over here, I don't think we've seen these yet in this class, but these are diodes. Oh, actually, we did see these a while ago. I believe Lab 3, where we had the quick project with an op-amp, where we were trying to turn on an LED, right, using our photoelectric resistor. So diodes are, or LEDs are a form of diode. So these guys are diodes over here. We've got another resistor. So a lot of really familiar components. Now, it's laid out in kind of a weird way. And the reason that it's laid out like this is basically just to separate out our circuit into individual small sections, which make it a lot easier and a lot cleaner when you're looking at it. Because if all of these were connected, it's a mess. So if we look, actually, you can see each of these wires has a name. So we've got 5 volt, 3.3 volt. This is ground, right? GND, ground. And now if we go over here, we can see this guy's named ground, this VDD plus over here. All of these are named as well, 5 volt, enable, input 1, input 2. So what's really nice about Eagle is it lets you essentially do nets of wires. So let's take, just for example, this 5 volt wire. So it looks pretty short. It just looks like kind of a stub wire. But in all actuality, it is part of a net. So it's named 5 volts, 5V. And if you see over here, this wire is also named 5V, right? Yeah, this guy here is also named 5V. And that may be the only 5V guys in this circuit. Oh, and there's another one over here, right? So all of those 5V wires are actually connected because they have the same name. We just don't have the actual physical connection being drawn between them. Now, if we did, of course, we could add it on. We could click onto the 5 volt net here, and then let's try to make it so it doesn't overlap with everything. And see, we could wire them together like that. But Eagle knows, because they have the same name, that they're actually going to be connected. It knows to connect them itself. So that's why we're able to separate out our individual pieces of our circuit into different places, and we can sort of have these net connections or these virtual connections between them that are just done by naming them the same name. It makes it really convenient to separate out your circuit. You can have separation of concerns. So, each section is worried about doing one specific thing. And it makes it really clean to look at and much easier to debug. So you're not worried about, where are these wires overlapping in case something's gone wrong. Nothing like that. It's just really clean and easy to look at here. Now, we also have some of these big blocks here with a couple inputs and outputs. These guys we haven't looked at so much or really at all in this class. These guys are called integrated circuits, or ICs for short, and they are typically some sort of small pre-manufactured chip that's going to do one specific thing for you, right? So this chip here, for instance, this is LM75A. You can see its name. This is a Texas Instruments chip. So LM75A is produced by Texas Instruments, and this is a temperature sensor and thermal watchdog, as they call it. Basically, what this means is it will read a temperature, and it also has this OS switch, this OS signal. This is going to be a single bit. It's digital, so it'll be either high or low, 1 or 0. And that will basically be like an emergency shutoff signal. So inside this integrated circuit, we likely have some thermistors and some really complicated stuff that when I was designing this, I didn't want to worry about doing that temperature sensing myself. So I decided let's just drop in a temperature sensor that's already made and that we know works well. Now, this guy over here, he's a little more complicated, and it's, I actually don't seem to have the integrated, oh, I do have it named here. So it's the L298. Now, this chip, I believe this is called, it's a dual full bridge driver is the type of integrated circuit there. Basically, this is just used to drive different loads, such as relays, solenoids, and in this case, we're using it actually in the circuit to drive a motor. So those are the two kind of integrated circuits that are interesting. In here, these other blocks that you can see that look like this, that are labeled J1, J2, J3, and J5, I guess. I think this one over here is J4. These are just input-outputs, I/O ports, right? So these are just pins where we could plug in a single wire to each of these pins. And so, yeah, that's how you label those on a schematic like this. Not trying to move anything. And so, as we have mentioned before in this class, a big part of doing electrical engineering is looking at data sheets, right? So that was one thing that's really important when you're doing the sort of PCB design, especially if you're using integrated circuits like those ones that I'm using in this schematic here. So this is an example. This is the L298. This is the schematic or the data sheet for that dual full bridge driver that I was talking about. So this data is really, really helpful. You can see exactly what's going on inside of the chip. We can see we have some logic gates. These are logical AND gates. We don't need to go too much into what that does, but it's basically a simple Boolean operation. So it takes digital inputs of either true or false, 0 or 1, and outputs a single digital output. It looks like these signals are going into transistors. Again, you guys will go over transistors more later. The main part of this that we want to look at here is just to see how you can actually create these circuits. So when we're designing circuits for a PCB, it's really important, that we see information about how much voltage it should be supplied, the sort of voltages and currents that it will output, and this will help inform us when we are trying to design around it. So if we're trying to, let's say we're trying to pick what resistors to put near it, we want to pick resistors that will work well with these voltage values, right? Now, typically and often, these data sheets will also have suggested wiring setups. So if we look through, this here is a suggested setup for using, let's see, yeah, this is using the full dual bridge. So this is using the full chip. And you can see it suggests that you put a capacitor here, a 100 nanofarad capacitor should go in parallel with our input here. And same thing here. Right, so this kind of information can be super helpful when you're designing because you can see exactly what the chip manufacturers want you to do with it. And you can see, what their suggestions are. And oftentimes, their suggestions are pretty good. So if you actually look at what I ended up designing in Eagle, you can see, so at VCC, at the 5-volt source here, from here it doesn't look like it doesn't look like I put in that capacitor, but remember, we have this other net with the same name, also 5 volts, with a 100 nanofarad capacitor right here. So we can see I actually followed their instructions, and I put that 100 nanofarad capacitor in parallel with our input to that integrated circuit, exactly like they suggested I should do. Great. So this is the basics of a schematic. I know looking at these can be kind of difficult to figure out what's going on, but the most important thing with a schematic is that you are showing what parts you plan to use in your circuit and how they should be connected to each other. Not necessarily where they should go, just how they should be connected to each other. Okay? So after I have written or made this schematic here, I can pop over to the board design. Oh, and a little more, sorry, I don't want to pop over there quite yet, just because I want to show just a little bit about how I actually made this. So it's actually really simple, similar to LT Spice. So we've got this button here, which lets us add a component. Oh, you guys can't see that window because it's not being shared correctly. Let's see if I can share that. Huh. No, that's not our component search, and that is not either. Okay, well, it does not want to let me share this component search here, so give me just 1 second to figure out this window. Okay, there we go. Now you can actually see this. So this here is a big, huge list of libraries that you can use, right? There's a lot. The easiest is if we go to this RCL library, which is resistors, capacitors, and inductors, RCL, right? We can click on RUS, which means the United States symbols for resistors. And now if I click on one, we can see sort of what it'll look like and some basic information about it, right? So this could be really important information if you were designing a really specific circuit. Let's see, you can see this grid takes up 5 millimeters. So if that was, we can see if that was too large for my schematic, that could end up being an issue. Oh, and there is an important difference here. So we have what you see here. This is a pretty classic resistor, as you've seen in a lot of this class, right? The circle shape, the barrel with 2 wires coming off of it, right? So these guys are called through-hole resistors. So what that means basically is that if you were going to put this on a PCB, if you were putting this resistor on a chip, what it would look like is there would be a little hole drilled in the chip at each side, and then the pins, the wires from it, would go through those holes, right? And then you would solder it onto your chip, onto those holes there, right? And so that's sort of like what we're doing with our breadboard, right? When we stick the pins into the breadboard, that's sort of like pushing it through the hole of the PCB, and then it's going to be connected to metal sheeting where it can actually become part of the circuit, right? Now, an important difference is, let's see if they've got some, okay, great. I believe, yeah, these guys are a little bit different. Let me see if I can find a better example of one. Okay, this one's pretty nice. So we can see it has a different shape now. It's more rectangular, and its footprint, so this is kind of like what it'll look like when we print it, also looks a little different. So this kind of resistor is called a SMD, or surface mount device. So rather than having wires that go through holes on the PCB, SMDs will, they essentially make just direct contact with the top layer of your chip, the top layer of your PCB, and then you solder them directly onto that. So there's no holes for SMDs. They don't have to go through and get soldered onto the back like through-hole components. Surface mount devices, you just solder them right on the face of your PCB chip. Okay, so that makes them. It could be a lot easier. It could be a lot harder, depending on what your application is. So once we figured out what resistor we wanted to use, and note there's a lot of different resistors, you just press OK, and just like that, I have a resistor. It has an arbitrary value. I can place it wherever I want. And then I could, right click and give it some properties. So, this is where maybe, let's see, if I wanted to give it a value. Oh, actually, sorry, there's a value tool. This guy over here. So I could click on this, give it a value, we'll say 10 k ohms. Now it's a 10 k ohm resistor. Right? That's not, the value there is actually not super important for doing PCB design, because when you actually fabricate a PCB, it actually won't have any components on it. Essentially, when you make a PCB design, you're saying, leave space for this component here, and then it's up to you to actually solder the component on. So the value there doesn't mean anything other than it's just a nice note for me when I'm reading this to know what size that resistor should be. Okay, so then we can move this resistor anywhere we want. And then we have a wire tool, it's called net, that we can use to wire it together to other components. So really, really similar to LT-Spice, actually, in this sort of 3D design way that we're using it. So once we get done with our schematic, oh, I just deleted some things I didn't want to delete. Okay, so once we get done with the schematic, we want to actually figure out how to lay these out on a physical board. So that's when we press this button here, which generate/switch to board. This changes our layout to this board view, which is a different window in Eagle. And I'm sure you can tell right away, it's complicated. What we're looking at is a mess. So there's a lot going on here. So when you first generate this, now obviously I have generated this before, and I have finished and done the layout for this chip. This is a fully designed chip. When you first do this, all of these components will just be off to the side, and because Eagle won't know where to put them. It has no idea. And so then it's up to you to actually place the individual components physically where they should be. And then all these red and blue lines, these are our wires connecting them. They're called air wires here. I don't know why. I think it's just the same as wires. So there's some really important things when you are actually making a chip like this, when you're actually laying things out. First thing to note is this has all the components from our schematic. Right here we have our LM75A. It's a little bit hidden behind these wires. It's a little hard to see, but we have our LM75A here. I can try and select the actual chip itself, but it only wants me to select the wires that are all around it. Let's see. If I grab the chip, there we go. There's our LM75A, so you can actually see the chip there. That's our temperature sensor that we were talking about before. Over here, this is the IC1, which is the other chip. This is the motor driver, right? The full bridge driver that we were looking at earlier. So yeah, this is their actual physical footprint, how the physical chips look. So you can see even on the schematic, even though our LM75A and the motor driver looked about the same size, on our actual physical board, they are clearly very different sizes. Now, all of these guys are either going to be, this looks like it's a resistor. This is also a resistor. I think some of these are going to be capacitors. Oh, this one's actually a capacitor, sorry. You can't really tell the difference from here, right? Because from the actual layout point of view, it doesn't matter, because the layout is not going to be placing, when I print this chip, it's not going to have these components on it. It just needs space for a capacitor. And over here, it needs space for a resistor, right? So it doesn't actually matter which it is, just that it has space for the thing that I said needs to be there, right? So placed all the things, and then routing is actually really difficult. So routing is where you actually go and you draw all these wires here that you're seeing, all of the red and blue lines. Sorry, that's this guy, right? This wire and this wire that connect different things. And so this is complicated because wires can't overlap, right? This is a single two-dimensional plane. They can't overlap because otherwise they would be touching, and that's a problem. Now, there's a slight exception to that rule, and that is that this PCB that I'm designing is actually a two-layer PCB. So it has a top and it has a bottom, right? So all of these red wires, these are on the top of our PCB. And all of these blue wires that are now highlighted, these are all on the bottom of the PCB. So, and you may notice at the points where the red and blue wires kind of meet, like right here, there's a little circle. So this is called a via. It's like a hole drilled in the PCB, the same kind of hole that we would be using for a drop-through component. But this is a via which is going to connect our top and bottom layers. So this allows you to do things like you're seeing what I'm doing here, where I have this VDD that needs to basically overlap with these two wires here, the motor red and motor black. So I took VDD, dropped it down to the bottom layer through a via, and then once it's crossed over those guys, it can pop back up to the top layer and finish the connection. Okay, so I hope all of that makes some vague sense. I'm trying to be really a rough overview here of what actually this circuit is. Now you can also do some fun things with circuits. You can put your name on. You can put arbitrary art because it'll just be printed, right? Whatever you put on here. I wasn't very interesting. I just put my name in my unit because this was for a class, so I wanted my name on there. So no real fun art for me. And yeah, oh, another thing here that actually you're not seeing yet. One of the reasons that in my design I tried to avoid, there are much fewer, if you notice, there are much fewer of these blue wires than the red wires. So there's much fewer wires on the bottom than there are on the top. And that is because the actual the bottom of the circuit I'm using is something called a ground plane. So essentially, almost all of that bottom layer is actually going to be connected directly to ground. And that's helpful for several reasons. Basically, it provides shielding for our circuit from interference from other things. And so if I have more wires on the bottom, that ground plane becomes less effective because the ground plane has to basically carve out a space. It's not part of the ground plane where that wire is. I'll try to, let me see if I press this. So you can actually see the ground plane here, this big blue blob. That's the ground plane. All of that is connected directly to ground. And you can see it has like a cutaway here for this 5-volt line, right? So that's not connected to ground because it's cutaway. It's not part of the ground plane. It's something else. And so if I had a bunch of blue wires, we'd have a bunch of places where the ground plane is cut away, and it wouldn't be all that effective. Okay. So that was a really, really broad overview of what is going on with PCB design. This kind of stuff you could end up doing a lot. And if you guys are more interested, please talk to me or Ben. I know both of us we're in the same class, so we're doing a good bit of PCB design right now. So feel free to talk to us. If you want to download Eagle, that's the software I used here. It's Eagle by, oh my gosh, by Autodesk. That's the company. You can do that, and you can mess around, and you know, there may be some cool opportunities to mess around with PCB design and actually make your own circuit. So the last step with this PCB design is once we have finished everything, we want to generate it. So we've got this button here called Generate CAM Data. Yeah, sure, let's save my design. And if I go through this, it will create a zip file with all of the data with all of the different layers and all of the different information that's needed to actually print this chip. And then you can send it off to a manufacturer, and they'll print it for you. It's super cheap. I think when I did it, it was, so I went and printed this chip from a company called OSH Park, or Osh Park, maybe. I don't know. So I went and did this. They typically give you 3 chips in a single order, just in case there's any defects with any of them. And it was like, I think it was like $8 when I did it. So it's super cheap, right? Chip fabrication is very cheap, and it only gets cheaper if you're buying in bulk. So just to show you, I did mention I went and got my chip printed. So I actually have it. It arrived just the other day. It is right here. It is tiny. It's tiny. It's actually 2 by 1 inches here. And you can see, hopefully, it looks exactly like that schematic that I designed. We've got all those holes and all those places for different components in the right place. Now, I just have to go through and I have to actually solder everything on. But you can see they left little bits of exposed copper there. That's the more shiny parts. Those are exposed copper, which means that's where I can solder things on, right? And you can see If my camera actually focuses, which it might not, you can maybe see my name in the top right corner there. So everything that I put in my design ended up printed on this physical chip. So I've got a couple of these guys now. So now my next step is just going to be soldering everything on. And now I actually have all the pieces that I'm going to be soldering on in this bag here. So I can just show those to you guys as well so you can see a little bit more about actual physical chip design, because it is a little bit different than what we have been doing in this class. First thing to note is that this is in a shiny bag. This is a static dissipative bag or static shielding bag. I talked about static dissipation in the previous lab, in lab 6. Just sensitive components can be really sensitive to static discharge, right? So this bag, if you have static electricity built in you and I touch it, it'll discharge the static electricity in the bag and it won't actually reach the components. So that's just how circuit components are often shipped, because, they may be really sensitive. So let's look at some of the things that we have in this bag. So this guy here, this is actually a pretty big integrated circuit. This is that motor driver, the head, or the bridge header, full bridge driver. That's what it's called that I was talking about. And so you can see actually in the PCB, it is designed perfectly. There are holes exactly for this chip. They drop right into it. And now all that's left. And so this, you can see, is a drop-through component, right? Because the pins go through my chip. They show up on the other side. If I pull them out, you can see there are pins going through my chip. So this is a drop-through component, and I'll just have to solder it on there to make those connections. Now my other integrated circuit, that temperature sensor, that one is much, much smaller. Let's see if I can find it. It's this guy. So he is in. Oh no, I dropped it. Oh, there he is. Okay. Whew. Thought I lost it forever. This guy is tiny, tiny. He is actually inside of this little tiny pouch here. So when I'm not going to take it out now because, as you saw, I just dropped it and that could have just broken this forever. It's this very, very tiny component that will fit exactly on the little place right in the center of this chip, right there, right there. That's his place. And then again, I can just solder that guy on. And you can also see, let me try to reduce the reflection. You can also see that most of those, especially that smaller integrated circuit chip, does not have holes on it. So it is not a drop-through, right? That is a SMD, or surface mount device. The other guys that we have here, let's see, what are these? They are very, very small. So this here, let's see, I don't know if you can even see that. It's very, very small. This is actually one of our resistors. So it's again inside this pouch because it's super small and I could drop it and lose it forever. So this is one of our resistors. You can see these SMD resistors look pretty different than what we're using before. I do have one other component that should look pretty familiar, and that would be this guy. It's just one of our capacitors. We've seen capacitors before. This is, of course, because it has wires coming down, this is a drop-through component. And so we've actually got another place set up for that guy on the chip. And it should go right there. You can see its wires sticking out. So I'll have to put that in, clip the wires, and solder it on. So yeah, that's some rough basics of what we're doing with chip design here and what kind of product you can end up with when you're done with your PCB design. And what the differences are from what we're doing in lab between what we actually end up doing in real life as engineers, as whatever you want to be doing with this electrical engineering stuff. So yeah, you often want to use your lab tests with our larger components and with our breadboards to verify something so you don't have to go through designing a whole chip and getting it printed and paying $10 and waiting for it to ship, only to find out that your chip is wrong and that you designed it wrong. So, test things with the breadboard, build it there, then design your schematic based off of that. Then get one of these little fun guys and take some really, really tiny components and put them all together just like that. And so our benefits here are, of course, size is one of the huge benefits of using a PCB. This is tiny. It's 2 by 1, 2 inches by 1 inch, 2 square inches, which is much smaller than just about anything we could build by hand. You saw how small all of those components are, which are obviously not something that we could be using in a lab type scenario. They would just get lost or broken immediately. And so, yeah, this is how you end up with chips that are going to be powering larger electronic systems that you'll be using in the future for robotics or for mechatronics or anything like that. So please let me know if you guys have any questions. This kind of PCB design stuff is super interesting, and I would love to help you guys figure it out if you have interest in doing it on your own. You can download Eagle for free, I think. I got it for free as a student, so I think they just have a free version, or you can use your student email. I don't remember. But if you're interested, definitely check it out. Let me know, and we can design some cool circuits and get yourself a PCB, and we could get it soldered, and you can have your very own, very small circuit, just like that. Awesome. Thanks.